We give coding interview preparation, technical talks, workshops, and a bunch of other technical events to prepare everyone here at UA for going into the field. We're very happy to have Kitware here tonight. They're an incredible company, and we actually have a few people that we know who work for them. Kyle Edwards is a good friend of mine from the UAlbany Discord. And with that, I'd like to pass things over to our moderator tonight, Emily, who's going to be asking most of the questions and as well as introducing our panelists here, essentially. So thank you.
Hi, I'm Emily. I'm the Director of Outreach. I've been speaking with Dr. Villa about coordinating this whole event, and we're very, very happy that you're all here tonight. We're very excited to see a little more about how Kitware works on the inside. And I believe you have a presentation to show us first.
We do. Thank you very much for inviting us. We're happy to be here and to speak with you and tell you a bit about us as a company, what we do. We'll have several people from Kitware from different of our teams to dive in a little bit deeper into some of their projects. And feel free to either throw questions in the chat or, however, I don't know what the normal way of getting questions out, but feel free to interrupt us if there's something you want to know immediately, or we'll definitely stop for questions at the end as well. So my name is Lisa Avila. I'm one of the founders of the company, and I'm the CEO. Oh, let me start my screen sharing so you can see my slides. Okay. So we are a software R&D company. We're located in Clifton Park, New York, just a little bit north of UAlbany. We've been in business since 1998. We have 5 founders. We were all working together at GE in the Research and Development Center. We were working on some open source software that we developed as part of a textbook that we had written while at the R&D Center. And so we were able to get that software out as part of the textbook, and it was with a BSD software, a BSD license, so that anybody could use it and modify it, redistribute it with no license fees. This seems very common right now, but back in the 90s, that wasn't amazingly common. There were several big visualization systems out there at that time that cost thousands of dollars per seat to be able to use them. And we put something out that, to start with wasn't as powerful as those, but it was free. And that took off really well in graduate schools and research labs. And we got a lot of people coming to us to do collaborations on some really cool projects. And we decided to start a company around the visualization toolkit, VTK. So that's actually still going now, that open source platform that we have. So it predates our company. It's older than the company. So we started that probably in 1994. So we had this visualization toolkit, and we started a company around it, and we thought we'd do the traditional software thing and do services around this open source product that we have, do training and support and custom development, but that we would also then take any profits that we got from that and funnel it into developing commercial products that we'd then keep proprietary and license and sell to people, because that's how software companies worked. But it turns out you don't actually have to do things the same way that everybody else does. And we found out that we had a talent for doing the research side of software development, always finding the next new problem that somebody needed a solution to that hadn't yet been solved. And having our open source platforms out there was a great way of bringing people to us, because they got a great following out there in the world, and people would come to us and say, this almost solves this problem I have. Can you help me get it to the next step? So people came to us like the US National Labs and said, this is really great, but we really need it parallelized to work on the world's fastest supercomputers. And the National Library of Medicine came to us and said, this is great, we need you to develop something just like it, but to be used in segmentation and registration for medical images. So we began developing these relationships of forming open source platforms, building communities around them, supporting those, and then using those to develop the next set of technology. So we have a company that's focused on science, technology, and innovation, and not on IP. So we don't patent things, we don't protect things with proprietary licenses. And for the most part, as much as we can, we give things away for free. And that allows us to have an emphasis on collaborating with others. And that really brings us into some really big collaborations with other organizations that allows us to be part of problems that need many organizations to work together to solve. We're part of the exascale computing project that is working to bring our computing abilities in this country up to the exascale. And we get to be part of that in this model that we have of being a very open science, open technology company. So we work in a variety of areas. We started out in focusing in scientific computing with our toolkit that was focused on visualization. So it visualizes a variety of different types of data that you might have, mostly things in 3 dimensions or 3 dimensions plus time. And these might be very big. They might require being parallelized on a supercomputer. We do a lot of work with data that is generated through simulation. So that tends to produce enormous data sets. Imagine doing things that are simulating something, at the size of the universe, trying to understand where all the dark matter went to, or across the globe, trying to understand how the climate is changing over time. And so we work on the end-to-end workflow of that. So we might work with the data as it's being created or as the parameters are being set up. It gets fed off to the simulation system, and then it comes back into our software, and we work on visualizing it, analyzing it, slicing and dicing it to let the domain scientists really understand that data and draw conclusions from them. We have our medical computing team that grew out of that, because you have data that you're visualizing, and sometimes this data comes from medical scanners. So we work with things that come out of MR scanners or CT scanners or ultrasound data. And that needs to be visualized. It needs to be analyzed. You have to look through and understand, is there a disease present in this data? If there is a tumor, what size is it? Can we keep track of that over time to see if some treatment is allowing it to shrink, or is it still growing? We work in areas such as surgical planning. So if we're going to go in and do a surgery, can we take that data that we're looking at and plan that surgery ahead so that we have less time on the operating table for somebody? We work on training the surgeons. This is a lot of fun with robotic devices that provide force feedback. So you can simulate doing laparoscopic surgery and doing suturing, and get a chance to practice that before doing it on a real patient. And we're going to have Rachel come in and do a deeper talk on some of the things that we're doing in our medical computing team. We do a lot of work in computer vision. This is an exploding area. You probably have a lot of classes there at Albany on deep learning and data mining and other things like that are using AI algorithms. We do quite a bit of work in this area on looking at videos and understanding what's going on. So what's in the video? Is it trees? Is it grass? Is it sky? What's happening in that video? Are there people walking? Are there cars driving? Are there bicycles going by? What sort of activities are happening? Did a person come with a box and hand it off to another person, and then there was an exchange of something that happened there? Did somebody drive up, take something out of their car, put it down, and drive away from it, and left that item there? So these are things that you can imagine with hundreds and thousands of hours of video that go by. You want a computer to be able to automatically understand what's going on in these videos, to understand where there might be a security risk. We also do a lot of work in image and video forensics. And that's very key these days with a lot of fake news out there. So being able to tell whether or not a video or image has been doctored in some way. And we're going to have a couple of folks from our computer vision team, Matt and Daniel, speak about some of the work that we do in that area. We also have a data and analytics team that works with data from taking it in and doing any cleaning that you might have to do. Very large data sets usually have some cleaning that needs to be done before they can be analyzed and visualized, and then doing the analysis and the visualization to draw conclusions from it. And this might be data that is bioinformatic in nature. So maybe information and images related to some disease. They could be data that is geospatially located. So maybe you're analyzing and trying to draw correlations between the migration of mosquito populations and the spread of the Zika virus. So there's a lot of work there on the tools that go around managing and processing and understanding this data. And then underlying all of this is our software process tools. And many of you might be already familiar with CMake. It's used to build most of the world's C++ projects. And it allows you to be able to build a C++ project across a variety of different platforms, Windows, Linux, Mac, and not have to worry about what platform you're on. There's also tools for being able to do the testing and the inspection of the testing through dashboards to be able to do sort of a continuous development process where you write your code, you test your code, you check your code in, it gets run across a whole bunch of systems, you look at what goes wrong, you fix that, and it allows for better ability to develop code and see what goes wrong really quickly and fix it, rather than trying to only test things when you're going to put a release out. So across all these teams, one thing that we do is write a lot of open source software. We develop open source platforms in a variety of different areas. You'll hear about some of them tonight. We have some that have been around. As I said, VTK has been around now for 26, 27 years. That is probably more time than some of you have been around on this planet. And in the software world that you are now in, you probably realize how unusual that is. It takes a lot of work to keep these software platforms relevant and updated. Many tens of millions of dollars have gone into these to keep them going over the years and keep them functioning and up to date over that time period. But they have strong communities around them. Many of these are used in medical products that spend years in development and then years in production and then many years after that in use. So they need very long lifespans to be able to support that sort of applications. So at this point, I'm going to turn things over to Rachel.
Hi, everyone. I am Rachel Klipp. I'm a technical lead at Kitware. As Lisa mentioned, the medical computing team focuses on a lot of different areas, from surgical simulation to computational modeling to image analysis and on and on. I'm going to focus on a couple of areas. My particular area of focus is computational modeling, and so I'm going to start with our computational physiology platform, the Pulse Physiology Engine. Pulse has been around for, I think, 4 years now. It is spun out of another project we had called BioGears, which I developed at another company with a couple of colleagues. It was around for about 4 years prior to that. So the total age of this software package is about 8 years now. So not quite 20, but we're getting there. So physiology, when I talk about it, is focused on tissues, organs, organ systems, all the way up to the organism level. So from a human perspective, it's from your organs, like your heart and your lungs, all the way up to the full human body. We don't focus on the genetics, the atomic level, cell generation, or anything like that. But what we do is we represent the human body through lumped parameter modeling, which essentially means we use resistors and capacitors to represent how the body performs during healthy states, disease states, when it's injured, how you treat it. And so resistors represent the resistance to flow through any kind of vessel, so through a blood vessel or the airways, for example. And capacitors represent the ability of those to expand and contract, so to dilate and constrict. And that's the same for your blood vessels or your airways, for example. Lump parameter modeling computes pretty quickly. It's a 0D model as compared to things like three-dimensional modeling, which operates on all three axes, but it can take hours, days to compute. Ours actually operate faster than real time, which allows us to pair it with simulation technology. Our model is able to represent fluid mechanics, the diffusion properties. So we represent gas diffusion between the respiratory and cardiovascular systems, the drug diffusion between the tissues and the bloodstream. We represent things like your feedback mechanisms, responding your flight or fight response, for example, drug behaviors, how you consume and produce substances so that you have energy to move, run, perform, and then also how your body reacts with the environment. So for example, your body reacts differently if you're on Mount Everest than it does if you're in the desert deployed as a soldier. It performs differently if you're submerged in water. And so we have to account for all of those different environmental effects. Next slide. Our software is built with multiple layers. So we implemented it all in C++, and it produces real-time patient information. One instance of our engine is representative of one patient. So you can kind of think about it as anytime you're using the Pulse engine, it's how you would treat a patient in the hospital. So you can do things to the patient and they can respond just like they would if they were a live patient or a mannequin trainer. The way we do that is we have the Pulse Physiology engine, which is all of our computational modeling. So the differential equations, the circuit solver, and the matrices, all of that stuff is one layer. It's wrapped in what we call a common data model, which gives common definitions for things like a patient, a substance, a drug, which allows us to add additional drugs. So if we want to have morphine and fentanyl, I have a common definition for those, and I only have to change the properties of that drug. So it's diffusion across the blood-brain barrier. We just change that number, but we don't have to rewrite the entire program to use a different drug. And then we have a software interface, which is how you input and output information to and from the engine. And through that interface, you can then write a custom application. We do those sometimes in Unity or the Unreal Engine, which then allows people to connect them to trainers. You can also connect to hardware. So sometimes people use a Raspberry Pi to represent information or to control different actuators, or they connect it to a mannequin to allow for simulation on the mannequin and provide vitals to that mannequin. We also have a lot of documentation. We spend a lot of time doing methodology reports, which is not necessarily common with a lot of computational modeling, but we describe how each of our models works and provide all the verification and validation data with our models so that people know exactly how accurate they are, when they're failing, how they're failing, and what our plans are to fix that. Next slide. So talking about model validation, we validate on multiple levels. We validate on what we call a compartment level, which is at your organs or a specific blood vessel, the aorta, the brain, the kidney. And we validate pressure, flow, and volume. So these are all the calculated values. So if we have resistors and capacitors representing the body, then we calculate the pressure, flow, and volume in those systems. We validate all those, we provide our references, and then we actually color code the results. So it's really easy at a glance to see how we're doing. We also validate at what we call the system level, which is more your vital sign output or the values you'd get if you go to the doctor's office, your heart rate, your respiratory rate, your blood pressure, your oxygen saturation. And we do the same there. We use literature values to validate, and we color code the results. But then we also have to validate anytime we introduce an injury or an illness to the patient or we treat the patient. And so what we do there is we build these matrices, which you can kind of see small in the right lower corner. And so at these, we do timed intervals for what our action is. So maybe we do a hemorrhage or a tension pneumothorax, we let it run for a specific period of time, we pull all of that values and test those against values we found in literature. Or if we couldn't find values in literature, we compare it to clinical expertise. And so that's how we validate each of our different actions. We call them in the engine. And then we also stack all of those actions so that you could do a hemorrhage, a tourniquet, give the patient morphine, and also maybe an IV of fluids. And then we test all of those in combination to see what we think will happen. Next slide. So then we have a verification and validation suite. So as it was mentioned earlier, we do a lot of testing, a lot of automated testing. This is an example of that testing. So we build our code every night and after every check-in, and then we get automatic reports like you see on the left side. And I get these in my email every day that basically tell us not just how we performed against our validation data, but also how we perform against our gold standard data set, which is basically how we think the engine should behave. We save off that data and compare it every night to that same data to see if any of our check-ins have broken the code, so to speak. And so that's what the yellow and red is. If we get something that fails, I get a red email and know we have to log in and fix it. And so we run hundreds of scenarios every night and test thousands of variables. And these charts are a little out of date. I need to update them. Now we have approximately 90% of our values pass in less than 10% error, and less than 10% have a fail or less or greater than 30% error. Next slide. And so here are some examples of pulse in action. So our code basically produces data just in text files, and then it has to be visualized in some manner. And so one of the ways we do that is through what we call our Pulse Explorer. And Lisa, I don't know if you can play the video there. I had trouble getting him to connect on the left side.
This one's video.
Yeah. There we go. So this is our Pulse Explorer. And basically, this is a tutorial that's on the Vimeo website if you're interested in looking at it. But what you can see here is that we've visualized the data on a vital sign monitor, just like you would see in a hospital or a doctor's office. You can load up different engine states. You can pick your patient. So this is us stepping through, and you can load up some of the engine states that come with the engine. It stabilizes, and then you'll see the vital signs appear. There's a data request tab, which allows you to pull additional information. So maybe you're interested in the plasma concentration of the morphine you injected. And so you're able to actually look at that data as well. You can use the Pulse Explorer to set different actions, like this is us specifying a hemorrhage, I think on the leg. And then you can run faster than real time or at real time. And as you run, you'll actually see the patient start to deteriorate over time. So for a hemorrhage, the heart rate will go up, the blood pressure will go down. If you run long enough, the oxygen saturation will also drop. And eventually, if you don't treat the patient, you'll have cardiovascular collapse and the engine will stop running. So you can probably stop the video and we can look at one of the other things. Another way you can interact with the engine is through, like I mentioned, Unity and the Unreal Engine. And that's, for example, in the center shot here, it's actually integrated with a Unity application we built with another team. So it's a military application where they're at a point of care, or not point of care, sorry, they're at definitive care setting. So in the hospital, Pulse is running and you can view the results on that small monitor there in the center. And then they go through treating the patient through the Unity game, just like you play any other video game. And then they have a point structure tied to it. Another example is the image on the right where the combat medic is treating the patient. This one was built in Unreal, I believe, and they're placing a tourniquet. And when they place the tourniquet, the hemorrhage slows, the patient starts to recover from the hemorrhage. Next slide. The other area I wanted to quickly touch on, and I'll go quickly, is craniomaxillofacial injuries, which is something one of our other technical leads works on. These are injuries to the hard and soft tissue in the face. Due to the opioid crisis, this is a growing problem. However, it's very expensive to treat and it's not included in Medicare. However, it affects mostly the low socioeconomic population. So it's kind of a problem in the sense that you don't have healthcare to cover it and you also don't have money to pay for an expensive procedure. Next slide. So one of the problems is the image analysis for teeth right now is that you look at a 2D image, which doesn't capture the 3D nature of the injury very well. And so they're looking for ways to better quantify the injury, where it is, and how to repair it. Next slide. So cracked teeth is one of the most common problems. When you get a crack in your teeth, that the symptoms can come and go, which means that they don't always get treated really quickly, but bacteria grows in the crack, which causes pain and injury and can actually damage your entire jaw. Next. So one of the ways that our team has been looking at this is ways to segment the tooth, which is actually to isolate the 3D structure of the tooth, and then to analyze to find the crack. And so cracks are a high frequency component, but not as high frequency as noise. And the normal tooth is a low frequency component. And so you use a spatial frequency analysis to isolate the crack in the tooth. Next slide. To quantify that, they use wavelet theory, which is similar to a fast Fourier transform, to kind of quantify how large the crack is and where it is in the tooth. Next slide. And so to test these methods that we've developed, we actually induced cracks in teeth and then used the wavelet analysis and looked at the results to see if our method was reliable. And this is an ongoing project. I believe she just applied for another NIH grant to continue this work as well. Next slide. Another aspect of this work is segmenting out the jawline or different structures in the face or skull. And this allows the doctor to determine, or the dentist to determine, whether it's disease or actually healthy aging. So that's another high interest. And then we use also that same data for surgical planning. So this is another simulation tool where you can analyze and see how shifting the jaw forward will affect things and similar procedures. Next slide. One of the ways to do this is with statistical shape analysis, and I won't go into all of the methods here because I'm running out of time, but there's a lot of different segmentation algorithms that are used, non-spherical topology, and things like that. And so they allow you to isolate different components and statistically analyze them to determine if they are injury, aging, or a foreign structure that shouldn't be there. Next slide. And then we use a lot of these methods to actually build surgical simulation and training programs using one of our other programs, the IMSDK platform. So a lot of our platforms are actually networked together. And so we have something called Slicer Salt, which does a lot of the CMF procedures, which ties into Slicer as well as IMSDK, and IMSDK and Pulse are actually linked together so that you can do surgical simulation with physiology in it. So it's kind of nice in that all of our software structures tend to work together to build a larger programs that are more focused on a specific area of research. Next.
Thanks, Rachel. And one thing I didn't mention when I was doing the introduction, I did say that Kitware was founded in Clifton Park, New York. That is where our headquarters are, and about half of our people, or maybe a little bit more. But we also have an office in Carborough, North Carolina, and that's where Rachel comes to us from, and Daniel as well. And we have offices in Santa Fe, New Mexico, Arlington, Virginia. We're about to open one up in Minneapolis, Minnesota, and we have one in Lyon, France. So we're in numerous locations, and we spend a lot of time on video calls like this, talking to each other. So now I'm going to turn it over to Matt and Daniel, who are going to talk about computer vision projects at Kitware.
Okay, thanks, Lisa. So as she pointed out, Daniel and I are both software engineers in the computer vision group. And we deal with a diverse range of video and imagery analytics problems. Traditionally, our department has done a lot of work with defense and intelligence organizations, but more recently, we've been delving into other fields, such as environmental conservation that we're going to present on today, and a couple other applications, such as deepfake detection. A deepfake, for those of you who don't know, is basically a video which has been modified with deep learning algorithms, which might be on high-profile individuals, such as politicians or other people. We're going to roll through these slides fairly quickly just to give you an overview of our work. But if you have any questions, feel free to ask at the end. But in particular, I'm here to talk about VIAME, which is an open source toolkit that we're currently developing alongside NOAA Fisheries and a couple other collaborators. It mostly aims at detecting different types of marine species, both underwater and from the air, which I'll show a few examples of in a minute. Next slide. Fisheries, I guess, being the section of the government that handles quotas and rules for who can fish in certain regions around the U.S. So within our borders anyway, simultaneous rules for marine mammals protection in different areas. They're basically the government arm of that, and they have a small enforcement division for that as well. So that's where most of our work in this domain is with, but we have some others with a couple other conservation organizations too, such as Craniomaxillofacial Farms. So VIAME has had a couple different focuses over time, but what it eventually evolved into today that it's seen the most use in sort of a do-it-yourself AI toolkit that biologists or really anyone can use to generate their own machine learning models without programming experience. And this takes the form of both web and desktop interfaces. Most of its current use so far has been on sort of the first 4 items in that chart, particularly object detection and tracking. But more recently, we've been expanding it into stereo measurement, so fish measurement, image enhancement, image registration for generating mosaics and things. I'll show this in a second, and a couple other fields such as 3D model generation. Lastly, it has some evaluation tools for evaluating the performance of these algorithms. No algorithm that I've seen yet in this field is perfect that can classify every fish successfully. There's always some misclassifications. I think that's true across the board on deep learning. It's pushed the bar a lot with computer vision and what computer vision can accomplish, but there's still mistakes. So it's an ongoing process. So there's evaluation tools in there too. Similar to other open source things like Kitware, though, VIAME is provided open source. People can go in, they can download the source, edit it, they can download the binaries, install the binaries, and we now have Docker images for the web containers too. Next slide. So people have begun applying VIAME to a diverse range of different data. Some challenging problems shown here. You can see a lot of different camera variants here and some different platforms. Most of our work so far has been sort of underwater and in the air. So most aerial surveys are going for things like, if you see on the bottom middle there, there's very small specks. They might not be coming through your monitor, but those are seals in the Arctic in both thermal and EO skins. And you do sort of concurrent modalities there just because optical doesn't really cover everything when you're going for small objects like this. So you want to sort of fuse that with the thermal signature. Some people do that. Some people just do sort of monocular optical cameras. So like the sea lion next to that for sea lion counting. So that's one end of the spectrum. The other is basically underwater fish counting. Typically people are going for the order of 100 to 200 fish species in a given region. And they're basically using this to generate classifiers specific to their region, such as the Southeast fisheries in the Gulf and sort of the middle there. Next slide. I think so far we've seen the most success with scallops anyway. That's currently going basically through accreditation for use in the official counts there. It was originally created as sort of an integration platform, though. Before it had these interfaces, that's sort of where its history lied. Basically as a way to connect up C++, Python, or MATLAB nodes together. So there's a little bit on the toolkit for that. There's basically baseline classes for things like object detectors or trackers, et cetera. And it was originally funded basically with a representative from each of these fisheries science centers around the US, shown in that figure there. Next slide. Has basically 3 different workflows for generating these types of models. Not going to go into them in too much detail here, but say you just have raw imagery that has no annotations, you can annotate that. And by annotation, I just mean drawing, boxes around the imagery saying this is fish type A, fish type B, et cetera. So you do that over and over again until you have thousands of examples, train a deep learning model, rinse and repeat until you're happy with the model. That's like the most traditional deep learning workflow. But then there's sort of 2 auxiliary methods. One is you run existing detectors that are similar to your problem. You use that to bootstrap annotation. The other is this rapid model generation process that doesn't always work. Sometimes it does, sometimes it doesn't. Depends on how easy the problem is. But you give it one example of what you're looking for, and then you do adjudication through your results. And I have a quick video on this later on if we have time. Next slide. Typically, it goes for three or four types of annotation. You might have frame level properties, which is, is some type of object present in the frame. You don't care about how many are there. You just care about like whether there's some effect at the frame level, yes or no. Box level is the easiest to do annotations for, though it's not always the best. It doesn't give you all the information. Pixel level, we prefer those types of annotations, but they're much harder to do, especially when you're talking about thousands of fish that these biologists are annotating. Key points, on the other hand, are useful for basically size measurement if you're doing head tail lengths, which in the fish domain, most of them are interested in that. Next slide. So it's evolved to have a couple different interfaces online. One of them, viame.kitware.com. Anyone can go to these days, log in. It's free to make an account so you can try things out without installing. But it's basically an open annotation archive where people can go and run some existing pipelines that we've trained up for different groups, do annotation on new pipelines. Then there's a couple of different desktop interfaces that are a bit more specialized to individual customer needs. but at the same time, you can do annotations in them. We now have a desktop version of that web interface too in the main desktop package, which is basically using the Electron framework to package up a web app as a desktop interface. Next slide. So these are just some capabilities overview. I'm not going to go into the technical details too much, but if you're interested, feel free to reach out afterwards. But on the detection side, we use some open source frameworks such as PyTorch, TensorFlow, and a couple other in-house things too. Basically for making ensemble detectors, so taking two detectors from two different frameworks and then fusing them together for better performance. Again, because generally one of these things isn't perfect by itself. So that's pretty common, but doing things like hyperparameter tuning, typically when you're training networks, there's some high level parameters you need to set, trying to set those automatically or training multiple ways so that biologists don't have to set them. Next slide. Rapid model generation is an alternative way to generate models fast in the system. Typically, this is, you give it one example of what you're looking for, and then you go through a procedure called IQR where you check off what was right, what was wrong that the system proposes to form what we call low shot generation, where you're generating models from as few samples as possible. This procedure typically has two stages. If you're familiar with Google image search, that typically has two stages as well. There's a caching stage that looks in your entire image archive and basically creates a summary representation of it just in a smaller form that can be queried quickly. So that's typically an offline process that creates basically a summary of a video. We call them descriptors over different subpatches. And there's an online user in the loop stage where a user is provided an example of what they're looking for. It's matched against this archive, and the user can interact with the data faster. Next slide. So this is just a video of that procedure. That indexing stage that I talked about previously has already been done. So this is on an archive of like 20,000 images. And maybe it took, I don't know, maybe like 5 hertz or something. So 5 images per second to process that archive ahead of time. But now the users found one example of what they're looking for, a flounder there. It's very distinct by its pattern. You can see, the system's providing some example flounders here. Top 20 results. That top panel there are things that are most similar to the query. The bottom panel are things that the system's more uncertain about. So the user can go through, check off what was right, what was wrong, and then basically use this to rapidly create a model. So it should show the lower panel in a second. Flounder are very distinctive here. If you look at the bottom panel, the uncertain things, you see you get rocks and things that look like flounder that aren't flounder, like that example there. It's very flounder shaped. Flounder is a particularly easy example, though. This tends to only work on things that are very distinctive. In some of the harder problems, such as classifying 200 species of fish where the genus is very similar, you don't really want to use this approach. It's going to break down because the descriptor that it's using isn't powerful enough to handle that. Next slide. Oh, video just doesn't want to stop. That's one application. Basically, there's not too many people who have used that in production. Most of the people have used the first method, which is sort of ground up annotation, deep learning training. But some groups have used that to bootstrap their annotation process. So they rapidly generate a model, they rerun that on some new model, and then they use that to correct the annotations before doing deep learning, which can be helpful. So another thing we're doing is 3D model generation here. This is mostly to aid with scallop detection. So, is a scallop on the seafloor or is it swimming above? Next slide. Object tracking comes into play a lot because you don't want to duplicate count your fish. This also comes into play in helping the user do annotation. So there's what we call AI assisted annotation, where the user draws a box on the start frame of a track, presses a tracking button to fill in the tracks faster in the annotation process. Next slide. Registration and mosaicing comes up, basically, again, to prevent duplicate counting. This is more common in the aerial imagery. Some people want to generate mosaics for the sake of the mosaics, but others use it for not counting the seals twice. Typically, there might be like a 30–40% overlap between neighboring images in some of these aerial collects. So when you're doing a census of a particular population, you don't want to double count the seals. But this touches on some other work in vision, such as that interface on the lower right for a project called Telesculptor that my coworker Matt Leota is running. That sort of recreates the camera path of the aerial drone and comes up with a 3D mapping of the scene. Next slide. Full frame classification, and this is my last one here, I promise. This is typically for, is there a full frame event, such as the example here, which is, a GoPro strapped to a penguin head. Some of these weird applications I didn't even know existed until working with NOAA. But basically they're trying to detect, is there krill in the camera feed, or is the penguin surfacing? So that little plot underneath there is sort of like the density of, was it above the surface? Was it underneath the water with no krill, or was there krill in the feed? Basically for krill assessment. But full frame is also used for things like substrate classification. Is the bottom rocky or is it sandy? And then predicating species detections on top of that. Next slide. Stereo measurement, I'm not really going to go into, but we have two methods for that, a pixel classification method and a non-pixel classification method. Next slide. Lastly, I'm going to pass it off to Dan here, but so some people are comfortable basically doing collects in their labs. So they collect a massive hard drive of data, they bring it back to their labs, and then they run it through VIAME to do the counting and whatnot. But other people want to do it closer to the sensor system. So actually on the airframe itself, and then on that side of things, they can curate the data a little bit before it even lands. They could come up with initial counts. Eventually, the goal is to not collect all the imagery, to only actually save the imagery that has targets of interest in it. But with that, I will hand it off to Daniel.
Thanks, Matt. Yeah, hey everybody. My name is Daniel Davila. No relation to Lisa Avila. Just very, very close names there. Yeah, I'd like to tell you a little bit about the work I do over in the CPS group. CPS here standing for Cyber Physical Systems. We tend to do a lot more project work that's focused on kind of the fusion of both open source software, but also hardware, which is kind of puts interesting spin on things, because as Matt said, a lot of these data science projects stereotypically, involve going out and collecting a bunch of data, bringing it back to your lab, running your workflows on a big beefy server, and that's the end of it, right? And you deploy this back to maybe a cloud or something, something with like Lambda scaling or what have you that can ingest infinite, if you believe the hype from Amazon, data flows, right? No matter what they need to sync the demand. But there's a lot of use cases where you do not have that resource available. The most notable one being sensing applications on the edge. So the edge computation movement, this is a big buzzword that you might hear a lot about. Pretty much just means running deep learning and other types of workflows on resource constrained hardware on the edge, on a drone or something, right? So here's a pretty concept figure for a program called ADAPT that we're running currently. We just started our phase 2 actually. If anyone wants to hop on board and help us out, that'd be great. This is funded by NOAA, who's one of our collaborators, as Matt just went through. They have a long, rich history with them. And the aim of this project is to do this work I'm talking about, where we migrate an interesting and useful deep learning algorithm out to the edge. In this case, a small unmanned aerial vehicle, or SUAS. Next slide, please. So to motivate the project a little bit, I'll give you some history. So this is the Yukon River in Alaska. Up there north, the weather gets pretty ugly in the winter, like real cold, to the point where the Yukon River, which is just an absolutely massive river, we're talking about 2,000 miles in length, and upwards of a mile at the widest point it's crossing, it just freezes over in the wintertime. The whole thing freezes. This is bad for a couple of reasons. When that thing starts to thaw, particularly when all the snow around the river starts to thaw, you get this huge inrush of water into the river, putting a lot of hydraulic pressure on that cap of ice that sits on top, and you end up getting what's called fracturing, where, as it sounds like, the ice just starts breaking up and flowing downriver. The problem with this is that if all that ice floating in the river hits a choke point where the river gets narrower, the flux, the matter trying to go through that choke point is huge. All these huge ice blocks that can't go anywhere before, because the river's pushing it. All the might of the Yukon's pushing it forward. However, there's a choke point, so the water starts rising and flooding. The issue here is that with that flooding, because ice floats, it carries icebergs the size of small houses out of the river and onto land. And in 2013, there's this terrible disaster that a lot of hydrologists are studying to this day in Galena, Alaska, where if you look at this picture, the Yukon River here, you can actually see it about a mile away, 2 kilometers away in the background. And in the foreground, I'm highlighting here a couple icebergs the size of minivans that are just rolling down Main Street, just flattens houses. Luckily nobody died in this incident, but it was very sudden. They did not see it coming, and it caused a lot of damage and then displaced a lot of poor people. So our effort, we're actually trying to detect these ice buildups and breakups using a drone in real time, so that we can provide some mechanism for decision makers to get real-time feedback on the conditions in the river. Next slide, please. The reason why we're using drones is that the next best thing is satellite imagery. Again, because this river is just so huge, you can't monitor the whole thing very efficiently. You pretty much have 3 options. You either have somebody out there in like a Jeep or a helicopter, literally walking back and forth the entire 2,000-mile stretch of the river, looking at it. You use a satellite, which is what you're seeing in the middle image here, which is way too low resolution. You can't really tell anything that's going on in that image. Or you fly a drone of some type, which is what you're seeing on the right-hand side. So this is an image of the Yukon River in January timeframe when the ice first starts to break up. And the problem with this is that the drone can't fly but so high and take so much of an area of picture. So this imager is 4K imager. It's only getting a 400-meter wide stretch, which is pretty good to capture the river with. But assuming that you could use this imager to image the entire width of the river, to run the entire 1,700 kilometers of this river, you have to monitor visually. A human themselves will have to monitor 4,000 images a day without any kind of automated help to check every single segment of the river whether there was some potentially catastrophic buildup of ice or breakup of ice. So again, that's where we come in. We're trying to automate this process of looking at these images coming off these drones and say, is there something dangerous here that we should be paying attention to? Next slide, please. So what we did is with our collaborators at the University of Alaska at Fairbanks, so Dr. Peter Webley specifically, a real great guy up there. They went up there and flew a bunch of drones in the freezing cold for us and took all these pictures of ice buildup and breakup during the winter months, which you're seeing out here on the left. And what we did is we hand annotated a lot of these images. By we, I mean a bunch of poor grad students up at KU have annotated a bunch of these images pixel by pixel to indicate where there was ice or snow or vegetation or water. And what we did is we trained a deep segmentation network on this portable rave machine back here to automatically segment out these images to say where's their water, where's their ice. So what we can do with that model, as you see in the bottom right of that quad chart there, is we can find pieces of ice that are disconnected from other larger pieces of ice. What that indicates, and what we're seeing here, you can kind of even see it in the visible side, is that there's an ice chunk that's broken away from the pack. That ice chunk there is about 100 meters wide. It's a very big piece of ice. And that could be the start of this traffic jam that causes the flooding event later on. So this would be an example of an alert that gets sent back to HQ so that the decision makers, people at the NWS and NOAA, can make arrangements they need to save lives in the future. Next slide, please. As I mentioned briefly, the system is actually interesting from an open source perspective because we have this stream of it being not just an open source software, but an open source hardware system as well, meaning that all the hardware designs as well as the software will be available for download and improvement upon in the future. There's an open hardware movement out there. I know if a lot of you are aware of that. I know open source software gets all the love and it's great, but open source hardware is a thing too. Someone's mic is on. I'm sorry. Yeah, thanks. So yeah, the rise of open source software has created this concept of an executable paper, right? This idea that when you publish a work, there should be a link at the very bottom that you can click on and run some code and reproduce the results. We want that for this project. So we want someone to be able to, I don't know what's called, maybe like a buildable paper or something, but we want someone to be able to go download the parts they need, well, buy the parts they need, download the software they need, stick it together like Lego bricks, and go fly their own, ice detection mission and iterate on our designs. Next slide, please. Yeah, in the interest of time, we can actually skip this one, the next one. All right, yeah, that's all I had. With that, I'll pass it off to Bill.
Okay. Hi, I'm Bill Hoffman. I'm the CTO at Kitware. I'm one of the founders. I've been working with Lisa on this Kitware thing since 1998. We started the company in 99. And right in 99, we got some work with NIH. Go to the next slide. And that led to creating this CMake project. And it's one of the really cool things about working at Kitware is that although we're a relatively small company, we kind of punch above our weight and put out software that's used by, millions around the planet. I mean, it's really cool. So recently, Jetbrains, that makes an IDE, did a survey. They've been doing every year. CMake's been getting more popular, but it's at about 53% of all C++ projects are using CMake now. And another interesting thing we've noticed is that CMake experience is required or at least mentioned on somewhere around 500 jobs on Indeed and LinkedIn. So that's kind of neat to see as well. Go ahead and go to the next slide. So where did CMake come from? So we had this project with the National Library of Medicine, who created this data set called the Visible Human Data Set, which was a body of a man and woman that were, after they died, they CT scanned them and MR scanned them with the best technology of the day. But then they froze them solid and sliced them as thin as they could and took actual pictures. So this gave a really good set of reference data that the National Library of Medicine put out for researchers to use. And around 98, I think this came out around 94, yeah, 94, 95, the data. And then in 99, a man by the name Dr. Terry Yu kind of came up with the idea of, well, we've got this great data set that we've given to the public, but really what we need if we want to advance science is we want to take the state of the art in segmentation and registration and codify it in a usable computer language. So let's create a C++ library, and we'll hire people that know how to do open source software. So they had 3 commercial vendors come in, and then 3 universities come together, and we all work together to create this toolkit. And we were essentially tasked with making sure that it built on Windows, Mac, and Unix. And by Unix, I mean like Sun workstations. That's how old this was. Linux was just starting out back then, and it was definitely around, but was less of a powerhouse than it is today, of course. So in 99, we, I guess the official first CMake 1.0 branch was created in 2001. But the ideas of CMake started around 99 with this project. Go ahead to the next slide. So as this has gotten more popular, interesting projects have come across our plate to work with CMake. For example, we've had a recent project where the Minecraft team is using CMake, and they came to Kitware to add some new features to it. And that's been really cool to work with those developers and to see the wide range of usefulness that the tool has. And another really shocking surprise that I never would have guessed when I started the project is that Visual Studio from Microsoft has adopted CMake and adopted it in a big way. Now Visual Studio 2019 comes bundled with CMake as a build tool. And I'm pretty sure when I started creating CMake projects for Visual Studio back in 2000, they might have sued me for reverse engineering their file formats without permission. But then by, 5 or 6 years ago, they came to us and actually hired us to help them integrate it better into Visual Studio. Microsoft changed a lot, and our software has adapted. So go ahead to the next slide. And this adaptation, I mean, this is something that Kitware has been doing, and the 5 founders of Kitware have been involved in, since the mid-90s to late 90s. And it's commonplace today, known as continuous integration development, but wasn't so commonplace back in early 2000s. And the idea here is that software developers, they work on their code and they check it into some common repository. And then there's an automated system that pulls that code out as those changes are made, and then runs that code through a battery of tests, and then produces some sort of dashboard or visualization of the current state of the software for those developers to see. And it counts things like, number of build errors, build warnings. It can run powerful static analysis tools or dynamic analysis tools that look for memory leaks and buffer overflows, and it can compute code coverage to make sure that your tests are covering all the code that you actually write. And having this feedback system allows the developers to make big changes to code and allows that code to develop. And I think that's one of the main reasons that VTK and a lot of our software from Kitware has such a long shelf life. We're able to go in and make absolute massive changes to the software and be assured that the test suite still works, which means that our people using the software, their code's still going to work too, as long as that code coverage is really high. And it's one of the unique things about Kitware, that we're developing this software that has all these users. We don't even know who they are a lot of the time. We just know we sort of work with the tip of the iceberg. But we've created this business model where we're able to collect up various customers and have them each contribute to a piece of a toolkit. And then that, through all these different customers and Kitware focusing that effort, we can build tools that are much greater, and the return for everybody is much greater. And this is how scientific software needs to be advanced. I mean, if you look at a modern car and just go scroll through the entertainment system, and you look long enough, you'll find the copyright section, and you'll see BSD licenses and GNU licenses and how to download the source of the software depending on the license. And basically, you can't build modern, complicated machinery and software without using open source software. And Kitware is sort of one of the engines for that. So we get to play in that field and to work on a lot of really neat projects, from fusion reactors to fission reactors to the world's biggest supercomputers. This sort of software process and all these tools get to be applied. I think that might be the last slide. Yep.
All right, thanks, Bill. And then just to wrap up a little, perhaps you're thinking about joining someplace like Kitware in the future, and I thought we'd just tell you a little bit about what we're looking for in candidates. So as you've probably seen from what we've presented, we do a lot of work in research and development. And on the research side of things, what it means is that we're presented with problems and we have to figure out how to solve them. So it's not like your class project where somebody sort of laid out what the steps that you have to do. Somebody kind of tosses you what they need to be done and you're not quite sure how to get there. So we need people who have background and skills in doing that. And one of the best ways of getting that is to get involved in some research projects. So you might be able to do that by finding summer internships to work on research projects, or around SUNY Albany, there's probably professors looking for people to work on their research projects. So having that research experience is very helpful. And our best candidates are often involved in various open source communities. And there's lots of them out there. They're usually looking for people to contribute to help find bugs or add new features. And so, I definitely encourage you to go out there, find something that you're passionate about and get involved in an open source community. And the people that we hire generally have a strong passion for what they do, and it really shows. So, there's something that they're really interested in doing, an impact that they're planning on making on the world. And they've shown that through the projects they've been involved in the open source communities they've contributed to. And then tossing out there, we do have an open source software technology program. This is something Bill started a year or so ago, where folks coming out of school with a bachelor's degree apply for this, and they come work at Kitware and go part-time to school to get their master's at the same time. And they rotate through our different teams and get a chance to work on all these different projects while learning about all this different open source technology. And so that is what I have.
Thank you for that presentation. That really went into a lot of things that I didn't even see researching the company myself. So that was really cool to see. And I'm sure everybody has a lot of questions if you're willing to talk a little bit.
Sure.
All right. I know Connor has a question first, if you want to go ahead.
Yeah, sure. Thank you, Emily. Hi, my name is Connor. I'm the vice chair of our IEEE student branch here. And I want to know, so obviously you started with CMake, but I want to know what makes you decide to take on a new research project? Is it usually companies reaching out to you, or does someone in your team have ideas of something they want to do and then they sell it to you basically? So how does that go down at your company?
It actually happens both ways. We do quite a bit of work with the federal government, and many times they put out solicitations about what they need solved. So they have a problem and they sort of describe the problem and the solution that they need. And many companies bid on that and put their idea of how to solve that problem and how much that's going to cost in a long proposal where you go through all the details of how long it's going to take and how many people are going to work on it and what you're actually going to produce. There's that sort of bidding against that work. And then on the flip side, sometimes people have been looking at our open source, they've downloaded it, they've tried it with their data or their problem, and they come to us and say, hey, we'd really like you to help out with this.
Okay.
Similar to, as Bill said, with Microsoft coming to us to help them out with CMake.
Okay, thank you.
Next up, I know Matt has a question.
Thank you, Emily. Sorry about that. My name is Matthew. I'm the communications director here for the University of Albany IEEE student chapter. And I just have a question about VIAME. VIAME is definitely one of those platforms that I really saw beforehand, before this panel. And I was really interested by it because growing up, I definitely in my spare time will watch a lot of stuff about like kind of like underwater, especially like killer whales. I love that stuff. And I remember I was watching a documentary and they said they really love to use drones to identify different species, or not species, but different pods of killer whales out on the West Coast and other places too. Also just reduces pollution and whatnot. So I guess my question is, do you guys with VIAME use things to like maybe identify different pods of like whales or other like species of animals that need to be, I guess, counted? Do people use that for that? I think of the whale population because that's one people always want to see.
Yeah, I could answer that. So the notion of whales, there's some interest in there. People haven't used VIAME too much for that yet. What we're talking to biologists about is doing that from satellite, which is sort of new. VIAME is traditionally applied on aerial and underwater, but there's an upcoming research program for doing that on right whales. So in the North Atlantic, they're endangered. Traditionally, they've done aerial surveys for that, but they're trying out basically with NGA a counting program doing that in satellite imagery as opposed to aerial, with the presumption that it might be cheaper. That's still up in the air. So that's one aspect of that. We definitely do a lot on the counting aspect of things for fish and sea lions and that much. We just haven't done too much with whales yet. But we do a lot of marine mammals. So sea lions up the coast of Alaska, off the coast of San Diego, a little bit in the Northeast, but not as much as out west and in the Arctic. The other area that whales comes in a lot is acoustics. So using sonar to detect whale populations as opposed to imagery. It's a little harder to do whales with imagery just because they have a really, really large area that they cover and tend to swim over. That's an area we're trying to get into right now is dealing with sonar a little bit more and processing sonar with deep learning techniques. It's not something that we've done a ton of, but it's potentially a field of growth for us. So.
It's really cool. Thank you.
Yeah.
Kind of goes back to the previous question a little bit in that, you know, if someone has a passion for something, you know, obviously Matt's very passionate about the marine life, and you know he'll go after that funding, you know, and look for that and try to make it work, you know. So that's one of the more interesting things about Kitware is we're, you know, when GE had a very sort of set things they worked on and companies they could work with, and it was very set and rigid, you know, whereas Kitware is a much more open place to explore new ideas and find different funding streams or do different types of work. I'm done.
I think James has a question.
Thank you, Emily. So my question is more directed towards the computer vision team. You briefly glossed over the fact that you have in-house software for hyperparameter optimization. Are you planning? So you guys mentioned you're using the standard stuff, TensorFlow, PyTorch for your models, right? So one of the biggest issues that we face here in the data mining lab is we have to do all of our hyperparameter optimization just through massive grid searches and trials and errors, essentially. And we've really been looking for an open source solution to that. So is there any plans to potentially get a open source hyperparameter optimization tool out anytime soon?
That's definitely a loaded discussion. You know, in the context of VIAME, you know, it's not too different from a grid search that we're using. It's just more of a grid search of parameter spaces outside of the context of the user having to do that. So it does that automatically under the hood based on how much time they have available on their GPU. Like they'll launch a model train and there's a maximum amount of time you can set in a configuration file, and it can try multiple, you know, hyperparameter sets in that time window. It's still not super, yeah, that Dan might definitely have some ideas here too. It's still not super good about estimating hyperparameters from like the data characteristics or being general beyond computer vision or these image analysis frameworks. We're definitely using PyTorch much heavier than TensorFlow right now in-house, although it varies on a project by project basis because some projects are for a particular customer and they have particular preferences. I'd say in general, our developers like PyTorch or even some of the C++ deep learning frameworks like TensorRT or DarkNet. But we're still a little biased towards PyTorch, but it's a bit across the board. I don't know, Dan, did you have any follow-up comments to that?
Yeah, James, I was just gonna say, have you looked into Ray.io at all?
I actually saw Ray.io while searching for solutions to this problem. I was really hoping that TensorFlow would have something built in for it, but that was actually on my list of things to look at next week. I made a list of all of the stuff that they had, so I was hoping to look into that. So
Yeah.
thank you. That's that could be very useful. I'm gonna write that
Yeah,
down.
so most deep learning libraries don't have great support for it. And honestly, what you said about like the block searching, grid searching, I mean, it's pretty much just the way it's done. Either grid search or do some kind of like Bayesian optimization on your hyperparameter space. The only difference between packages that implement solutions is how well they handle all the tracking of your experiments and documentation and how like lightweight they are. We've been experimenting a little bit with Ray recently internally, and we've had some pretty good results with it. Because we have a lot of internal packages, open source packages that do all sorts of training for you, all these crazy cool things. But this problem is quite a lot to wrap your head around, and this group at Ray.io has actually done a pretty good job from what we've seen. That's one thing that the wheeze that I've dealt with it. Kitware try to do is not reinvent the wheel. That's the beauty of open source software, right? If it's already out there, just go use it. Make it better if it's got some shortcomings. So yeah, we're looking at this package pretty hard, and we're probably going to be using it more and more.
That's very helpful advice. Thank you so much. I appreciate it. What's it like trying to glue together all of those open source projects? I imagine since most of your stuff is all of the, you're working so much with all of this open source software, even stuff that you haven't written, right? And there's a lot to fit together. So is a lot of what you do gluing together open source projects to try and get them to work in the framework of your open source projects?
Yeah, there's a lot of that. There's a lot of staples that people just get really good at using because they're titans of industry, like your scikit-learns, your NumPy, your Torch, all these different things, right? They're household names in this industry. But for some of the more niche things that we use, there's a non-trivial amount of the job that is honestly just hunting for documentation, just trying to figure out like what piece do we even need to glue into our thing to make use of this open source tool that like claims to do something right. That's probably one of the biggest shortcomings I think of most open source projects, and Bill could probably speak more authoritatively on that. But the ones I've ran into that I never want to use again are the ones that are not documented, that I cannot even figure out how to begin to use it.
I'd point out that a lot depends on the project too, on the integration front. There's definitely smaller, more applied projects and then larger DARPA projects. Those tend to give you a bit more leeway in one direction or the other. Like a larger DARPA project might have the opportunity to do a lot of ground up research, seeing what's out there, but then also analyzing, whether or not a new completely ground up software framework would supersede what's out there as well. Versus a smaller, more applied project, you might spend more time integrating what's out there and testing what's out there, and then gluing things together as opposed to doing novel research. So a lot depends on the size of the project too, and the scale of it, who the customer is, how much funding they're backing these things with. We definitely do on the integration side. We have a rich history in C++. Now there's a lot of this deep learning frameworks are Python based. That's not really true anymore because there are C++ ones now, like TensorRT and some of the things that are optimized for computing at the edge. So it's a mixture, but we do spend a bit of time sort of sometimes gluing C++ and Python frameworks together. And we have a couple of sort of frameworks to handle that. To say, take a C++ image and pass that into a Python array automatically, using PyBind 11 wrappers, and then getting the output from Python, passing that back into C++. It's a common occurrence that you might have a GUI or an interface that's coded in C++ or JavaScript. And so you're dealing with this cross language divide in Vision a lot.
I have a question from Robin, who unfortunately doesn't have a mic. Robin is our webmaster for the IEEE. He asks, he sees a lot of projects that Kitware does. When Kitware is trying to start a new project, how do you organize and plan out the project?
Well, some of that happens at the proposal stage. So if you have a customer that's going to pay for that project, you do some of the planning of it and estimation of the scope of it in conjunction with that customer. So you're getting an idea of what their budget is, because you can do a project from ground up, entirely new technology. You could and that might produce the absolute best results for that customer that run the fastest and are as carefully tailored to their problem and their data as possible. But that customer may not have that level of budget for that. So it's usually an iterative process of saying, well, we could this, or maybe this, it's a little bit bigger, or this that's even bigger. And you kind of get a sense from the customer what they're thinking of and what they're looking for. And you scope to that. Many times it's a process of having done something similar in the past and using that as a guide for estimating how long or how complicated something is going to be. Did you have something you want to add to this, Bill?
I mean, just from the software point of view, I mean, starting a new project is always, fun and exciting. And a lot of what we try to do is agile development, in that allowing for frequent releases of the software and getting feedback quickly from the customer. Many times we can get contracts that work out like that. Sometimes due to the funding vehicle, they may want to. Some companies like to know exactly what they're paying for and do a firm fixed price contract where we have to upfront figure out exactly what we're going to do, and that's exactly what they get. But even those, over time, the engineers manage to usually weasel those around and change some of the deliverables before the contract's over.
Yeah, sometimes it's great when we can do a prototype to start with. So we do something small that is sort of a proof of concept, and then we add to that. So it's an iterative process, as Bill said. So you're not trying to tackle the entire problem at once. You're taking a subset of it, or limited domain, or not worrying about how long it takes, or some aspects of it. And you're only solving it in a limited sense, and then you show how that works, and then you remove some of those constraints and solve that next problem and make it a little bit better and keep iterating like that.
That's great, thank you. I had a question about a lot of the medical imaging software that you talked about earlier. What kind of challenges do you find in trying to bridge that gap between accurately portraying medical procedures or health-related things and bridging that gap with technology?
So I don't actually work on medical imaging. I work on the computational modeling, so I can try and answer that a little more generally, as in when we're talking to customers about medical related problems and surgical related problems, you're talking to clinicians that tend not to have an engineering background. They tend to think of problems in a much more medical point of view, which is it's less science, more art, I would say. And we look at the problems from a much more scientific point of view, kind of what order do you do things in? What is your thought process for doing things in? We're much more linear thinkers, I think. And so the biggest gap when we start a project for medical is oftentimes translating what the clinician is saying into engineering speak and computer science language, and then working from there. So just finding a common language is often the hardest part to starting a medical project. Not sure if that answered your question, but.
No, that's great, thank you.
I have a question, actually. What are the inherent disadvantages of open source software, specifically security?
So can you elaborate a little bit more on why what about security that you would say is a problem?
I mean, I know like a little bit about, cybersecurity and things like that. I took like a year of it in BOCES, but I was just told that open source software is a lot more insecure and it's easier to find flaws or something like that.
So I think actually it really depends on the process you have around your open source development. Our open source packages, it's not that just anybody could come and check any random code into it. The code goes through a thorough review process where other developers look at that piece of code that somebody wants to check in and give their approval to it before it goes into the repository. So that does help a lot with that security issue. It would be very difficult for somebody to squirrel some major piece of code into the middle of one of our open source packages without us knowing it. I think on the flip side, the security advantages of open source are that there are multiple people looking at that code from multiple perspectives. And so it is much more likely that those issues would be found. than if it was a closed proprietary piece of software that you needed to rely on without being able to see what was happening under the hood.
Yeah, I think it's sort of a two-edged.
Go ahead.
Well, yeah, it's sort of a two-edged sword, right? So with open source software, people can find something and exploit it because they have access to the source code. But on the other hand, people can find the exploits and plug them up because they have access to the source code. So if you look at like the internet, I mean, you know, the SSL, OpenSSL, does all the encryption for, you know, your web browsing and all that, and that's an open source library. And it's occasionally they've found, you know, a 0-day issue with it. But I imagine if it was, you know, Microsoft's super secret encryption layer that the whole internet depended on, it would probably get exploited by somebody without anybody knowing about the exploit. And the end result of that would be much worse than everybody sort of discovering that there's this hole in the source code. So I would argue that it's more secure, done well.
Yeah, I have to agree. And to echo something and to emphasize what Lisa was saying earlier, you know, there's the nature of the industry is such that you cannot implement, for example, computer vision solutions without using some open source package, if not quite a few of them. And the reason that matters is that, you know, if you think about defense contractors, for example, you know, we do a little bit of defense work here at Kitware as well. The software they're building are being deployed to very secure spaces, right? You know, someone at some company, defense contractor out there is building object detectors and segmentation models and all the different things you see in academia and putting them onto drones and onto tanks and all these different things the Army uses, right, to do their mission. And those have to be very, very secure and robust to all sorts of attack vectors, right? There's this huge attack plane, especially with these like highly connected, you know, smart systems out there that they're using now. And, you know, like Lisa was saying, it's really all about the process that's wrapping the software, right? You know, you don't just willy-nilly let anyone commit anything they want, right? And on top of that, there are so many different ways to find exploits and vulnerabilities in software these days. I mean, we've automated the process like what 99.something%, I'm sure, just through like static and dynamic code analyses, code coverage, testing, all these different CI tools, right? That enwrap modern software development. You catch most of these exploits way before it ever gets deployed. And as you know, you have more users, like Bill was saying, and this we're saying, use the system, you test it, and, you know, explicitly in the field, and you find more exploits. So at the end of the day, you know, the software is as secure or not secure as you want to make it, no matter whether it's open source or closed source, really. But there are some inherent advantages to open source, as I said.
I think we have a question from Matt again.
Hi, kind of following up from Dan's question about kind of like the advantages and disadvantages of open source. I know I was looking at the Kitware GitHub today, earlier today, because I wanted to look a little more about CMake, and I was seeing all the stuff you guys have as far as you have right here. I have it up, the CMake issue tracker page, the like contribution document that you have, CMake discussion forums. You have all this stuff open source that really people are actively looking for bugs and trying to fix it. And I guess my question really is, you were talking about like the rigorous like process of trying to get something pushed to the software that you guys develop from open source from other people. You know, as far as like GitHub goes, and maybe I have something that I wanted to push, that rigorous process, what is that like for you guys when you're looking at something and being like, okay, maybe that's a good point, or something that we could actually use that in the software? How does that go for you guys, or how do you find that?
It depends on the project, but, you know, definitely as a project gets older, it gets more defined, and the bar for getting new software in gets higher. Mm-hmm. The older a project gets, if it's quality software, I mean, I think that's sort of a function. You know, at the beginning, it's sort of this rapid expansion and getting stuff done and sort of proof of concept and making things work. And then it settles down as the project grows, and then And also, I mean, I think today, the modern CI techniques are very effective. It was, in that someone can propose a feature branch, and that can be tested on multiple platforms before it's merged in with the rest of the software. And you can make sure that that all the tests that were working before still work, and that your code coverage didn't drop, and that all those. And then if there are issues with it, people can comment on it, and it creates a different way of developing software. I mean, it definitely you have to be able to get it by a group of peers to get your changes into the software.
Some of the open source software that we work on is developed primarily by folks at Kitware, and some of it is very collaborative with users around the world. And that usually starts out with somebody who is making use of that software platform, and maybe they start asking questions on the mailing list or discourse channels, and they then start, checking in bug fixes or small features, and we get to know them, and they get to know the process, and then they become eventually a trusted developer on that system.
Very cool. Thank you very much for your answer.
Sort of along that same vein, June wanted to ask a question. June is our social media director, and he wants to know, when interviewing people, what are some interesting projects you've seen in interviews where people use CMake? CMake.
I mean, we've seen all sorts of projects. I mean, I guess I'll answer it sort of to describe a little bit the interview process at Kitware. We asked the candidates to do a 30 to 40-minute presentation on, their education, their experience, and some interesting projects that they've worked on. I can't recall all of them, but certainly we've seen lots of interesting stuff, and it's good that it's nice when people have used our tools. It's definitely a leg up as far as getting a job at Kitware. But not required, but it definitely doesn't hurt.
Yeah, oftentimes people will tell us that they've been using CMake for a while, and then they came across Kitware and decided to apply, and then realized that Kitware made CMake. So it usually happens in that order.
Or it happens that you use CMake, but you did it all wrong, and then you get to Kitware and they fix it for you. Not that that ever happened to me. I'm just saying that's possible.
Purely hypothetically.
I think James had a question.
Thank you, Emily. So just to go back to one of the previous questions, do you feel as if open source software has basically the opposite problem that, the opposite problem would be a bonus. A lot of programming languages, especially C++, I know C++, C++98 is still considered like the gold standard, and some people consider it to have gone downhill from there with template metaprogramming and some of the latest versions and everything. So open source, on the other hand, what you just said was that it becomes more defined over time and really moves into its own space where you're able to really control the direction that the project goes in. Do you feel as if open source becomes defined enough so you would refuse pull requests like that would be asking to add features that you found added bloat onto the system?
Certainly you really hate to turn away anybody that's done something well with an open source project. So they can, and probably that's one of the things we have less control over projects at Kitware because of the way our funding cycle works, right? So we can't like set out a vision like, I want CMake to look like this in 5 years, and definitely, Kitware is going to set aside some money and that's how we're going to do it. It's going to be, I'd like to go in this direction, I'm going to try to find someone to fund me to go in that direction. So to some extent, we have less control over where some of our open source software ends up, but we are able to sort of control it from a high level and pull in customers that have interests that drive software like VTK or peer review in a sane direction.
I think with any project, over time it gets bigger and more complicated as it's handling more things, and then the ability to make the well, you're more cautious about changes that you make that don't work across everything. So when your project's small and you're going to add some feature and you have to consider how that works with every other feature, well, there's not too many others, and you can put that in and it's going to work. And then when your project gets bigger and more established, making some core feature change gets harder. And so it's much easier to handle the new features that can exist sort of on the side and on their own than the ones that are really going to change the core of how the system works. Because that backwards compatibility is important. It's being used by tens of thousands or more people out there who are relying on being able to get the next version of it and have their stuff keep working. So you just have to make sure that stays true.
I know I have sort of like one last question to wrap us up here. I know at least Lisa and Bill, you've been with Kitware since the start. I mean, you founded it. Would you say that Kitware has changed at its core kind of since you started, or is the mission statement kind of the same? Sort of like how you were talking about how open source can evolve over time.
Sure. Well, as I pointed out, we did start with the idea that we would be like other software companies and eventually create a product that we would sell and be more of a product company. We've stayed pretty much a services company. So we provide research and development services for people as opposed to selling something that we could just reproduce and sell licenses of. But I think overall we've had some, basic core missions to the company from when we started it. We wanted to be a company where we could do really cool work and have an impact in the world. So we wanted to be able to collaborate with other people and tackle the big problems. So that was always one of our goals, and that's stayed the same throughout all the years of Kitware. And then the other goal of ours was to have a company that was a great place to work, flexible and friendly to employees. And we've stayed true to that as well. Around that, obviously when we first started and there were 5 of us, it was an entirely different feeling than it is right now where there's, 220 of us around the world. We have a lot more, regulations that we have to work with now that we are working with things that are related to national security and things that are related to people's protected health information. And just with the size of our company, it does change some things, but overall we are committed to doing really cool stuff and getting it out there in the world for people to use.
Thank you. This whole presentation was very insightful. I'm going to hand it off to James to wrap things up here.
Thank you, Emily. And thank you again, everyone from Kitware, for coming. It's meant quite a lot to us at the IEEE here to have you guys show up. We know you guys are a massive company and you guys have a lot of great work, and it really means a lot for you guys to come out and give a presentation like this to aspiring engineers who are hoping to go into the industry within the next few years. We really appreciated looking at all the stuff that you guys had to show us. And we hope that in the future, we can get you guys back here again for some more presentations. Hopefully we'll get some better advertising and we'll have a lot more people next time. But we really appreciate it. For all of our IEEE members who showed up tonight, we have our side project development night tomorrow. So if you have updates to show off on any side projects you've been working on, feel free to show up. Next week, Monday, we have coding prep and interview prep on Monday. And we have our esoteric programming languages workshop on Thursday. Yes, Thursday. And an officer meeting on Tuesday. So be sure to show up to that if you're an officer. All right. Thank you, everyone. Have a great night. Thank you again for showing up, Kitware. We really appreciate it. Have a great night, everyone.